Hello class, welcome back. Today is lecture 12. So we've learned a few new techniques and now we're going to apply them for in a new situation. And that is with springs. Okay, so here is the idea. We are going to, we are going to start off with a spring. And you should just think about it as like hanging from like the ceiling or something. From a point, doesn't matter too much, but in pictures, something like this. You got spring hanging down, and it looks like that. So what we're going to do is then we're going to attach some sort of object to the end of it that has some kind of mass and see what happens. Okay, so if we attach an object with some amount of mass, which I'll call M, well, it's going to stretch the spring a bit. So it will stretch the spring to some equilibrium, meaning that, so I'll draw it right here. Oops. Attach the mass, meaning that, try to draw it at the same height, that now it's going to be a bit lower and there'll be some object attached to it, but it's not moving or anything. So we say that this is it's at equilibrium, it's stable, it's just sitting there. We haven't done anything, but it does stretch down from where it started. Okay, so then once it's in this position, then the party begins. Once in this position, you can get this, the mass, or the, you could think of it as the mass for the spring, but you can get it in motion by doing what? Well, by either pulling it or pushing it away from equilibrium, meaning, okay, it's nice and steady right here, just stays there. So then I can set it in motion by like squishing it up here and then releasing it, and it'll start bouncing down and up like that. Or I could instead pulled it down much further than the stable position, and then release it, and then it'll start going up and bouncing down like that. And I could also give it an initial push, which changes the velocity. But in this situation, what I'm doing is changing the initial position. So that'll come in later. Okay, but in any case, what do we want to do? We want to model the position of the mass or the object at any time t. So that's going to tell us the function that we're going to be solving for. The idea is I can do this game, I could start it in motion, and then the position of the mass, wherever this thing is, I should be able to figure it out as a function of time, so that if I plug in like 10 seconds, I can know exactly where it's going to be as it bounces up and down, stuff like that. Okay, so we're modeling the position. So that's what we're going to call our function that has derivatives and creates the differential equation. So this is going to be the position of the mass at time t. We're also going to need the derivative of position, which is velocity. So how quickly your position changes, that's how fast you're going. But we care about direction, so it's called velocity. And then the acceleration is also going to come into play. And that's the derivative of velocity. So we want to know how fast the velocity is speeding up or slowing down at any time t as well. So our differential equation is going to involve these three things. So p is our variable that sort of acts like y usually does. And then we're going to solve the differential equation to find p, or p of t. Okay. So let's write down some laws to get this differential equation. So we need some laws. Just write down the differential equation that goes with the situation. So the first is Newton's second law. So we've seen this one before, actually. I don't know if I called it this. But the basic idea is that the forces on the object add up to the total force. Force, which I'll call capital F. And that force is m times a, where a is acceleration, but now that's actually the second derivative of position. So that's what I'm going to use. Okay, so the total forces will add up to this thing. So I have something like F equals blank plus blank plus blank. And I got to figure out those other things. So what are these other forces that will add up to F? That's the next part. I guess I shouldn't call them other, just the forces. So the first one that we're going to have that's a bit different than other applications we've done so far is, well, we don't know what it is yet. So I'm just going to call it capital F of t. So it's just going to be some function of time corresponding to an external force. So the idea is you just have like maybe some sort of machine pushing it up or down. Something pushing, constantly pushing the spring up and down or something like that based on some function of time. Okay, secondly, the next force comes from Hooke's law. So this is a new force for springs that we haven't seen before. So the basic idea is that the spring wants to go back to equilibrium. So if it's down, if it's below equilibrium, there'll be a force pushing up. And if it's above equilibrium, there'll be a force pushing down. So it's always pushing against the position. And so it's called a restoring force. There's a restoring force, which we call F sub S. So this will always be present for springs. And it is equal and opposite to the forces applied to the mass. And more importantly, this is how we always figure it out. It's proportional to how much the spring extends or contracts as a result of that force. So the word proportional is key here. This is saying that the restoring force is, well, it's also opposite. So we're going to put a negative on it. So it's going in the opposite direction, and it's proportional to the amount that the spring extends or contracts. That's telling us that it's proportional to the position of the mass. Because how much the spring extends and contracts given a force. So if this is equilibrium and then a force makes it go down much further, let me just draw like this. And then equilibrium was up here. The idea is that equilibrium is when the position is 0. So if the position is down here, it's going to be a positive, something like 5, some positive number. Then the restoring force is going to push up. So it's going to be opposite of whatever's causing it to go down. So if something is causing it to go down, like gravity, that's causing this extension, then we'll have a little setup like this. So if gravity is pushing it down, which it is because there's a weight on it, then the restoring force is pushing back up, and they are equal to each other. And this will allow equal and opposite to each other. And this will allow us to solve for K based on how far it extends corresponding to that force that's pushing it down. Okay, so don't worry too much about that. We'll see examples and it won't be so bad. It sort of seems like the hardest part of these problems at first. Okay, and then the last thing is that there will be air resistance. First, we'll have no air resistance, but then we'll bring it in. So that's the third force. And we talked about this before when we did the falling body problem. So it's just proportional to the velocity, but it's always pushing against whichever direction the velocity is going. So it's going to be negative, and then another constant, I'll just use b because it's common, times the velocity because it's proportional to the velocity, which is p prime. Okay, it opposes velocity. If your spring is going down, then the air is pushing up, and vice versa. That's why we stick this negative there. Okay, so we got these three forces. And Newton's law says that they should add up to the total force F. So we have that there could be an external force acting on the spring. There could be there's the restoring force, and there's air resistance acting on the spring. So now plugging everything in, see, f of t is just going to be some function. We need it in a specific problem, we'll have it. So right now it's just f of t. But the other ones we now have from what I just did. So we get that, and it's a second order linear differential equation with constant coefficients, not necessarily homogeneous. And we can rewrite it as P double prime plus BP prime over M plus KP over M equals F of T over M. And we know how to solve these types of things. So we can then find the position of the mass at any time t. Okay, so let's do an example problem. Because the theory always sort of looks a bit difficult. So let's jump into a word problem here. I am going to break the word problem up into pieces. So this first, so you might usually see it as one big paragraph, but let's break it down. Okay, so a steel ball, so this is our mass, weighing 128 pounds. So just right off the bat, to remind you, pounds is a unit of force. So this is going to be some force. Is suspended from a spring which stretches it, the spring, 2 feet. So we're using non-metric units, whatever these are called, but that's okay. We're not gonna have to switch back and forth or anything. So stretches 2 feet from the natural length. Okay, so this is not the end of the word problem, but this is a good spot to use something to figure something out. So let's just draw this situation here. So what's going on is that all I have now, I haven't set it in motion. All I have is that I have a spring that's the natural length, and when I attach a specific steel ball to it, it stretches it from its natural length to equilibrium. This much. And so this is 2 feet. Okay, so this is going to tell us the restoring force. This is what we use to get the restoring force. We don't need the rest of the problem yet. We can just get the restoring force very quickly. So what does Hooke's law say about this situation? It says that there should be a restoring force corresponding to how much the spring stretches. And it corresponds to the force that is causing it to stretch. So what is causing the spring to stretch? Well, all it is the weight. And that's a force due to gravity. So the force due to gravity is 128 because pounds is already in units of force. So it's not in units of mass, common mistake, but in force. So there's 128 pounds of force pulling it down, and that corresponds to P equals 2. So notice we are considering down to be positive and up to be negative. So gravity is pushing down, so it's positive 128, and the stretch is going down, so it's stretching positive 2 feet. So now what we can say is that Fs equals negative 128 because it's equal and opposite to the force on the mass. The force on the mass is gravity. or the force on the spring, however you want to say it. Gravity is the force pulling it down. So the restoring force pulls it up at the same exact amount. So that's why it gets a negative. And it also equals this negative K times the amount that the spring stretched corresponding to that force. And this lets us solve for K. So people call this thing the spring constant also. But in any case, here it is. In this problem, K equals 64. Okay, so we'll need that later in the problem. This is not the end of the word problem. All this is telling us is Fs, the restoring force. So the key to getting the restoring force is using how much the spring stretches naturally or from its natural length to equilibrium corresponding to the weight. So we'll often have to do something like this. Okay, so now to continue the problem. So next, the mass is set in motion with no initial velocity. So nobody like taps on it or anything to get it going. But instead they just displace it, displacing the mass 1/2 feet above equilibrium. So this type of sentence is what tells us our initial conditions. Because what's going on is I'm determining the position that the mass will start at to set it in motion, and I'm also determining how fast I'm going to make it go when it starts. So in this situation, what we're doing is if this is equilibrium, I'm squishing it up a 1/2 foot. And because I'm squishing it above equilibrium instead of pulling it below equilibrium, this means that the initial position of the spring, so right at time 0 to start the motion, I am putting the spring at the position of -1/2. So we're going to use that later, and that the initial velocity, because I'm not giving no initial velocity, it's just going to be 0. That sentence is here. Okay, so this sentence corresponds to initial conditions. So with all our new techniques, we haven't really done many initial value problems, but it works the same as it did before, which is you solve the differential equation, and then you apply this stuff. To find some constants, because when you solve it, you'll get a 2-parameter family, and then we want to pick out one specific member of that 2-parameter family. Okay, so next, to finish the paragraph, assuming in this situation we're going to have no air resistance. No air resistance, find, so let's do 2 things, an expression for position of the mass at any time t, and part B, position. So this is just using what we're going to do in part A. And what is the position? Where is the mass at time pi/12 seconds? Okay, so we already know our differential equation, but now we just got to fill everything in. So there was no external force. So that is going to help us make things easier. So here's the solution. First, we're going to make everything easier. What's going on? Well, there was no external force. It's just the spring on its own. So that thing will be 0. There's no air resistance in this situation. So that thing will also be 0. Or you could just say, well, that means B is 0, the coefficient that was there for air resistance. So our differential equation for this specific situation just reduces to P double prime plus K over M P equals 0. So the air resistance is gone. The thing on the right is just 0. So we have a much simpler differential equation. Okay, so we already know K equals 64 from earlier. What about M? Well, to get M, we use gravity again. So the force due to gravity is the weight of the object. So all we're doing is this again. But we also know what the G constant is, but now we're in non-metric units. So it's not 9.8, it's 32 feet per second squared. Instead, when you're using feet, this is what G is. So M times 32 equals 128. So now I can figure out that M is 4. I can plug that in. Okay. So now I know my differential equation. P double prime plus K was 64 over 4. P equals 0. Oops. Plus 16. P equals 0. So this is a second order linear homogeneous equation with constant coefficients. So I can solve this with the characteristic equation. But before I do that, I want to sort of just think about intuition a bit so we don't get all lost in the math. So first, what should, if we do everything right, P of T look like? So what's going on is I have my spring that I've set in motion, and it's just going up and down, up and down, up and down, up and down forever. There's no air resistance. So it never like slows down. And so P of T should reflect the fact the position should reflect that the spring just goes back and forth forever. So it goes up to some position and then it'll go down to some other position and so on forever, never slowing down, never speeding up or anything like that. And that's what will happen. Okay, so let's see. So now let's solve it using the characteristic equation. Lambda squared plus 16 equals 0. Lambda squared equals negative 16. So lambda will be plus or minus 4i. Now, how do we interpret that as a solution? So we look and we remember that that means that the solution will be e to the 0i because it's a 0 plus or minus 4i, if you want to think about it like that, times C1 cosine of 4t plus C2 sine of 4t. So here is the position function, that we've now figured out. But now we need our initial conditions. Which remember we're P of 0 should be -1/2 and P prime of 0 should just be 0. But so far we already have that the position looks like a periodic thing because it's made of sines and cosines. So it just goes up and down, which is what we want, and it never stops. Okay, so that's what should happen if there's no air resistance and no external force. But now let's pick out our constants corresponding to our initial conditions. All right, so I'm going to need P prime, so I can use the second condition. So this is going to be -4 C1 sine of 4t plus 4 C2 cosine of 4t. I'll do this condition first because it's a 0 one, so it's much easier. So this tells me that 0 equals, if I plug in, oops, 0 for sine, that's going to just be 0. Cosine of 0 is 1. So I get 0 equals 4C2, so C2 equals 0. So then I can just plug that back in immediately to save myself some time. And then I'll use my other condition. So -1/2 equals C1 cosine of 4 times 0. This is just becomes 0 now because of C2. And cosine of 0 is 1. So I get C1 equals -1/2. Plugging that back in, -1/2 cosine of 4t, and the sine part is 0. This is my function. So this solves part A. And it goes with our intuition. So this is just saying that the position just goes up and down forever, periodically. So it reveals that the position has a periodic motion forever, which is exactly what it should do because it just goes up and down forever. So the graph will be a cosine graph. It'll look something like that. Well, actually, it's negative, so it's going to start down here. It'll look something like that at -1/2, and it'll go up to 1/2, which also makes sense because if I start the spring by pushing it up above equilibrium, where's my picture? Picture here. If I start it by pushing it up 1/2 foot and then I let it bounce up and down, it's never going to be able to go up past 1/2 or below 1/2 either. It's only going to go back and forth because there's nothing else pushing it further than that. So it's just going to go between there and here. Up and down forever, and that's what this cosine graph reveals. Okay, so that's part A. Part B is just saying, where is it after pi over 12 seconds? So just plug in pi over 12. And this will be that. So then it'll be up above equilibrium 1/4 of a foot. Okay. So now we're not going to do another example, but let's think about the next video, which will have more examples, and think about what kinds of things could happen. So what should P of t look like if there is air resistance? So then what we can imagine is I start my spring somehow by pulling it down from equilibrium or up from equilibrium. And then it'll start bouncing up. And then it won't bounce down quite as much as it started from because air resistance is slowing it down. And then it won't bounce back up as far as it went the first time. Then it won't go back down as far as much as it did before, and so on like that. So the graph of the function will do some sort of pattern like that if there's air resistance. So we can get something like this, where it looks like a sine or a cosine, but it sort of shrinks as it goes, as time goes on, because it's bouncing back and forth less and less forever. So when there's air resistance, we should get something like this. But what if there's too much air resistance is another question. If there's like way too much air resistance, then what can happen is it just doesn't even get a chance to bounce. It just sort of stops right away. So it's good to think about things like that. So that will correspond to when we have air resistance. So it'll correspond to different values of B, which corresponds to how much air resistance there is. So it should decay to a stop eventually. And then what about an external force? Well, then the idea is that P of T should eventually just follow the external forces, whatever it's doing. So if there's some sort of pump just pushing the spring up and down, then the motion eventually should just follow that external force. And that's also what we'll see. Okay, so in the lecture problems today, you'll see more examples like the one we just did, which comes down to setting up a differential equation. And then the easy part is actually just solving it with the characteristic equation because there's no external force yet. But the hard part is setting everything up. Okay, so, and then in the lecture problems, we'll also introduce some air resistance. Okay, so that's it for today. See you next time.